Hey there, and thank you for joining this course. This is the section number 4, Dictionaries and Sets, and I would like to make a brief introduction about what we're going to learn in this section. We're going to discuss in details what is a hash table data structure and how to implement simple hash table in C#. We will also learn about how to use a built-in C# class library hash table-based collections, and I will show you a couple of tricky things what might happen if you use your custom types in C# dictionaries and hash sets. So let's proceed to the next video where we're going to review a hash table in details. Alright, let's talk about a hash table. So what a hash table is? It was designed to address one very specific problem, a very fast item search of constant complexity. To achieve that, a hash table relies on hashing process, and this is why it's called a hash table. With the help of some calculation, which is usually called a hash function, we can transform our key or our item value into some unique number, and then we transform this number into a storage location inside our hash table. So to get access to the item that is stored into a hash table, we need just to perform some calculation, which will require this O1 complexity. I would like to emphasize that writing a production-ready hash table requires a very good understanding of computer science and math, and this is a very hard task. For the sake of this demo, our hash table implementation will be very simple. There will be no performance optimizations, dynamic resizing, and ability to use any objects as keys. We will to string keys, and this is made so you could concentrate on studying the core principles behind the hash table, so no unnecessary code would distract you from studying those principles. Alright, let's start with the following assumptions: that we have a collection of items, that each item consists of string key and any object value which corresponds to this key. And we want to design data structure which allows us to get an instant access to the value by providing this key. How can we do that? The first idea is to create an array and invent a hash function that will turn this string into an item index inside the array. Like this, for example, if we have this 4 elements array, 1, 2, 3, 4, and we have 4 items with keys words 1, 2, 3, and 4, and we invented a hash function that turned each word into a corresponding item index. So the item with the key 1 goes to the first element of the array, the 2 goes to the second, and so on and so forth. So far so good, but how can we add the element 5? There is no room left inside the array, and it seems that we cannot add this element. The first idea is to create something like dynamically resizing array to create a hash function that will always produce unique values for unique keys and perfectly maps them to the locations in this dynamic array. However, if we go this path, we will soon find out that it's impossible to achieve. And the problem that prevents us to do so is that arrays are hard to dynamically expand. We need to copy its contents, and if we want to add some more room inside in the middle of the array, you need also to split it up, and well, it's generally very hard to do so. Also, almost impossible to find a hash function that will produce always unique numeric values for unique string keys, and usually it will sometimes produce similar values for different keys, and we need to deal with it somehow. So producing similar hashes is called hash collisions, and dealing with is collision resolution strategy. So create our data structure, we need to deal with two problems. First, what to do with limited size array. Alright, we don't want to expand it very often. And what to do with those hash collisions, how to deal with items that are different but have similar hashes. Well, there are lots of collision resolution strategies out there, which has its strong and weak sides. And here we will review the simplest but also the least efficient strategy, which is called the separate chain with linked lists. So how it works? We create an array of items inside our hash tables, and those items are usually called buckets because they hold several values inside. Then we put into each item a reference to a linked list, which contains keys with the same hash. While this strategy is very straightforward, its main disadvantage is the same as the linked list's disadvantages are. So references hold lots of memory. In case for long linked list, you have to traverse it to find the right value, and the search becomes a linear complexity operation. Other strategies, again, are quite complex, and we will not review them in this course. However, in case you're interested to know about it, please let me know, and I will see if I can include this additional collision resolution strategies review later to this course. So let's try to illustrate how it works. Get our previous example where we have a 4 elements array of buckets, and each bucket contains one element. And now we want to add a new element, our hash table. So first we need to calculate hash code of the key 5, and let's assume that the hash code is 2. So this element should go to the bucket number 2, but the problem is that it already contains the element with the key 2. So what we do? We organize a linked list out of those two elements, create a reference from the first element to the new one, and when we are going to find a value corresponding to key 5, we again calculate its hash code, and it's 2. Now we're going to the bucket number 2 and traverse the linked list that is contained in this bucket. So we have to traverse 2 elements, and then we find a value under the key 5. But what happens if we add more elements and their hash will be 2 also? Well, we will have a long linked list, and the search operation will be on, which is something we definitely don't want because the search is slow and we need a fast search. Well, let's leave the problem of a slow performance for now. It seems that we almost ready to start implementing a hash table. There is one more question left. How to turn this string key into bucket number? How to calculate this hash? Well, each object in C# has getHashCode method that is designed to fulfill this task, and we can just call it and get some numeric hash value. And C# hash table based collections use this method to determine the item hash code. Writing a custom good hash function is a very hard task, so relying on C# default implementation is a good idea, but there are some tricks which I will explain in the next video that could lead into incorrect situation, and hash table based collection could work wrong if you use your custom objects wrong. We will discuss it in the next video. Well, so it seems that we can just call the getHashCode of our string key, but to illustrate how to write a completely custom hash function, let's use the key's first character code as a hash. It's not a very good hash function, but it will give you a general idea how custom hash function can look like. Now we have learned how to calculate a hash of a string key, but how to map it to one of the buckets in our hash table array. One of the ways to do so is using a C# integer remainder operator. And it works like this. An expression a%b, whatever the numeric value 8 might be, the result will be in range from 0 to b minus 1. And this is exactly what we want. If we use a bucket array size as b, then we get the mapping result from A to one of the array buckets. If you use a getHashCode method, hashcode might be negative, so after the mapping you need also to get an absolute value of the result, because arrays do not have a negative indices. And calculation might be like this, so you get the absolute value of a hashcode % bucket array size. Okay, now let's get back to a performance problem. Imagine if we have 4 buckets in our array and store some 1,000 items inside, so it's obvious that the search will be slow anyway. Whatever strategy we use, it's not enough to elements in the hash table array to store these number of items efficiently. So how can we understand if we need to expand our internal array? There is some criteria called load factor, and it can be calculated like this. Load factor equals n over k, where n is the number of entries inside the hash table and k is the number of buckets. So it's a well-known metric, and after some threshold value we know that we need to expand our internal array so our hash table will be efficient. Again, implementing a dynamically expanding and reducing hash table will require much more code and much more details. So we didn't do this in our example. We just implement the fixed size hash table because it's a completely different problem and it's not very much relevant to a key principle of hash tables. So again, we concentrate on how hash table works and leave aside all the implementation optimizations, all the unnecessary tweaks, so we can concentrate on the core principles. So now let's get to the implementation and see the code. So the first class that we're going to review is class node, because we use the linked list chaining for a collision resolution, and those linked list nodes will contain a string key, object value, and a pointer to the next node. Now let's implement the hash table. We implement generic class, which allows us to use any values, but we will use a string key. So we have an internal array of buckets, and since it's a fixed size hash table, we provide its initial size to the constructor, and there we initialize this array. Let's start with the add item method. What we do here, we provide the key and the value. First we need to validate the key. Here is our method of validation the key. If the key is null or white space, we will throw an exception because we cannot have empty keys. We need the key to have some value to be used inside the hash table. Okay, if the key is alright, then we create a new value node with the key and the value and the next pointer to the null. Then we get, by the key, we get the bucket which the items should go to, and then we see what the bucket array contains. In case there is no node yet, we just put the newly created node. But in case there is a node there, we traverse the linked list until we find the very last node and set its pointer to the newly created node. So we add the new node to the end of the linked list. Now let's see the get method. It requires us some more efforts. I will show you why do we implement it like this. First, validate the key, so there is no empty key. And then we use an internal method which is called getNodeByKey. It does what it's called. It gets a node inside the hash table by the key. How does it implement it? We again get the bucket by the key, get the first node of the linked list from bucket array, and we keep track of the previous item, because if we need to remove the node, then we need to know the previous item, and this is important. Pretty much the same as it was in the linked list. So we return a pair of values, which is previous node and the found node. Okay, so we go to the bucket array, get the item and the previous item set to null, and when they traverse the linked list one by one and look for the key provided to the method. And in case we find the node with the same key, we return a pair of values, previous and current node. If not, then we just traverse further, and either we will eventually find the node with the key provided to the method, or we return a pair of null values. Alright, so we found a pair of values, a node with a key, and this one we omit because we don't need to the previous node here. C# allows us to write an underscore, and we just do not use the previous node here. Okay, so if we don't found any node, it means that the key does not exist inside the hash table. In this case, we throw a new argument out of range exception, because we need to distinguish the situation when we store by the key an empty value or the key doesn't exist. Of course, we can do it without exception, but for the simplicity, it's done like this. I will show you how a system collection deals with this situation. Okay, so if we found the node, then we just return its value, and this is the get method. So we also implemented remove, where exactly we need the previous item. It works very same as get, but after we have found the node, we look what the previous node is. If the previous node is null, this means that the node was the first element in the bucket, so we just set it to null. If no, then as we did it in the linked list, we set the next pointer of the previous node, the current node's next, so the current will be deleted from the middle of the linked list. And contains key method implemented almost like the get. Look for the node with the key and return the logical expression if null isn't equal to node. Because if we have a node, then we contain this key in the hash table. If not, then we do not contain. And also the very important method is getABucketByKey, whereas this is the place where the hashing happens. So this is our naive hashing algorithm, like we get the first character of the key and then map it to our bucket array. We can use more mature mapping mechanism, but it wouldn't change the situation much, so feel free to experiment and comment out this line and uncomment this one. Let's see what the tests look like. So here is our tests. We create our hash table, which will hold ints, and initialize it with 4 buckets in the bucket array. Now to visualize what bucket will be used for each key, output bucket values for keys 1, 2, and 3. So as you may have guessed, the second and the third key starts with the same letter T, so they should have the same bucket number. Then we will add those value pairs. So with the key 1, we add an int value 1 and so on. And then we output items in our hash table. We look up by the key. So we test if our hash table holds items properly. The next test is to look for an unexistent key. In this case, we should get an exception and we output this exception message. And the last test is we remove from our hash table the items twice. And the first removal should output true because there was an element with this key. But the second one should remove false, and this means that we implemented a removal process properly. So let's run those tests. In a few moments we'll see results. And okay, we can see that the bucket mapping is like this. So the first key is mapped to bucket number 3. The second and the third keys have been mapped to bucket number 0. So then we print out the contents of the hash table, and this means that our linked list strategy have been implemented correctly because the second and the third items went to the same bucket. Now we print out the exception message, the key 4 is not found. And then our deletion method outputs true for the first call and false for the second call, because you cannot delete items twice. And the second call will return false because there is no such item in the hash table anymore.